This is section 4.2, number 15, part B. Same differential equation, non-homogeneous term. In part A, we were asked to try A cosine 3t plus B sine 3t, which I did in the previous screencast, and we found the A to be negative 8 over 145 and the B to be 9 over 145. But again, as this is our steady state solution, it's best to write it in this form, because now we can talk about the amplitude of the steady state term. There's no change in its period, but we can define the steady state term clearly. Here's its amplitude, phase shift. We can graph it easy. I made a point of saying that there's no reason why you have to use a positive amplitude. Should you choose to use the negative number for the amplitude, the phase change is different, and I calculated that in part A. And we're going to see these same numbers show up in part B. In part B says, hey, why not just start with the assumption that we're going to get our steady state solution, our particular solution, in the form of A cosine 3t plus phi. It's this plus sign that makes some of the signs a little different, but in the end everything's going to look the same. If this is our assumption, we have to take its first and second derivative. Let me put a p here. It's first and second derivative, and then plug this into our equation. So we go to the next slide where we do that. Here on this slide, here's our equation. You'll see that here's the second derivative term plus 3 times the first derivative term plus the particular solution itself, and all of that has to equal cosine 3t. Grouping terms together, I have a cosine 3t term here and here with coefficients of a and minus 9a for a total of minus 8a. And I have a minus 9a sine 3t plus phi. And again, the right-hand side is still cosine of 3t. I'm going to use the sum of angles formula for cosine and for sine. The cosine of x plus y is the cosine of x times the cosine of y minus the sine of x plus the sine of y. So here it's cosine of 3t cosine of phi minus the sine of 3t sine of phi. The sine of a sum of two angles is the sine of the first times the cosine of the second plus the sine of the second times the cosine of the first. So sine of 3t cosine phi, cosine 3t sine phi. And again, here's the right-hand side. Again, organizing things, since the right-hand side is cosine 3t, I want to find all the terms that have cosine 3t in them. So here's a cosine 3t, here's a cosine 3t. The coefficients are negative 8a and cosine phi, so negative 8a cosine phi. This cosine 3t term has a coefficient of minus 9a sine phi, minus 9a sine phi, all times cosine 3t. The other important term is the sine 3t, and these form the coefficients of sine of 3t. Equating coefficients. So here's a cosine 3t term with a coefficient of 1 in front. Here's a cosine 3t term. Here's its coefficient. So minus 8a cosine phi minus 9a sine phi is a 1. Similarly, minus 9a cosine phi plus 8a sine phi has to be a 0. I label this as equation 1, and this is equation 2. Multiplying, I want to clean this up, multiplying 1 by 9 and 2 by 8 lets me drop out the cosine terms, and I'm left with 145a times sine phi is minus 9. Doing the similar procedure to knock out the sine terms, I'm left with 145a times, that's a times, times cosine phi is -8. Well, if you looked at the Part A slide, this looks very familiar. There is a difference in sign, however, because our basic assumption is that we're working with cosine 3t plus phi, but you'll see everything works out in the end. Same thing we did on Part A. If I square this and add it together, I'm left with the statement that a squared is equal to 1 over 145, or a could be plus or minus the square root of 145. Next slide, last slide. Again, here is our differential equation. Here is what we are trying. So far, I've found that the amplitude can be plus or minus 1 over the square root of 145. And my relations with phi look like this. And this is exactly the same as what we went through in the Part A. The same procedure, but the numbers are a little different. In the end, they'll be the same. But in Part A, I can make a choice. Okay, if I work with positive a, then I divide through both sides by a, and I'll have two negative expressions. Sine of phi is -9 over the square root of 145. Cosine is a -8 over the square root of 45. Two negative numbers forces me into quadrant 3. That's where phi must live if its sine is negative and its cosine is negative. Taking their ratio, I get the tangent of phi, positive 9/8, but inverse tangent only returns things between minus pi over 2 and pi over 2. This answer that it returns is in quadrant 1. My answer has to be in quadrant 3. I can either add pi to this answer, and that'll rotate me into quadrant 3, or I could subtract pi from this answer, and that'll rotate me into quadrant 3. I choose to subtract pi because that'll get us a number that we'll be familiar with. This is what my phi has to be. And putting it all together, here's the form we're trying. A, we said, was a positive 1 over the square root of 45. Phi, we found out to be this negative number, but since the form is 3t plus phi, we get this, which is identical to what we had in Part A. This is one of our solutions. And then similarly, if, and I don't recommend the need for doing this, but it does make something a little simpler. If a is a negative number, coming back over to here, dividing through by that a, dividing through by that negative number, causes both of these expressions to be positive. And so in this case, if a is negative, the sine of phi will be a positive, and the cosine will be a positive. That means phi must be an angle in quadrant 1. Taking the tangent then, taking the ratio of sine over cosine, gives me 9/8. I find the inverse tangent of phi. I get 0.8441. That is in quadrant 1. And so I don't have to adjust the phi. In my second case here, my particular solution, same as in Part A, looks like this. So if I use a negative amplitude, this is my phase shift. Positive amplitude, this is my phase shift. This is what I recommend, but they're both correct, whatever you like. Okay, good luck. Thank you.